Hi, this is Baifeng Shi from Peking University. Today I will present our work, Auxiliary Task Reweighting for Minimum Data Learning. This is joint work with Judy Hoffman, Kate Sianko, Trevor Darrow, and Huizhen Xu. In this work, we will focus on this problem. Supervised learning is really data hungry or data inefficient. For example, to train a model with a decent accuracy, we need like millions of images. Towards this problem, people have come up with lots of settings and algorithms. For example, few-shot learning, transfer learning, semi-supervised learning, weakly supervised learning, and so on. But what we focus on in this work is another way, that is, if we can reduce our data requirement through multitask learning. So here is the setting. First, we have a main task, which we care about, but we don't have enough data for this. And meanwhile, we have some auxiliary tasks, which are relative or irrelative to the main task, and we have plenty of data for these tasks. So what we want to do is to utilize the data from these auxiliary tasks to train a good model on the main task. Here I should notice that this setting is a bit different from traditional multitask learning, because in traditional multitask learning, we want to reach good performances on every task, but here we only care about the main task. Actually, this setting is quite general because lots of specific settings can fall into this category. For example, in semi-supervised learning, we don't have much labeled data, so we design all kinds of supervision on those unlabeled data. Or in domain adaptation, we have plenty data in some source domain and we want to generalize to some target domain. Also, in reinforcement learning, the pure policy learning is actually sample inefficient, so we need some auxiliary tasks to help it converge faster. So all these problems can benefit from algorithms in the auxiliary task setting. So with this big picture, we will naturally have two questions. The first one is, by how much can we minimize the main task data requirement using the auxiliary tasks? And the second one is, how do we know which auxiliary tasks are the most relative to the main task? To answer these two questions, we will first start with the single task scenario, that is, how much data do we need if we only have a single task? In single task learning, we normally optimize a loss looking like this. The first term is the data likelihood of the training data, and the second one is some ordinary prior. Usually this prior is quite weak. For example, it's like a zero mean Gaussian if we are using weight decay. So this weak prior actually reflects our weak knowledge about the true parameter distribution. And meanwhile, we also assume that there is a true prior, which the optimum parameters theta star is sampled from. And normally this true prior is more informative, but we don't know what it's like. Here is an illustration of the two priors. The big one is ordinary prior, and the small one is the true prior, which centers around the optimal parameter. So, what does it have to do with the question before? Imagine that if we know the true prior, and since this prior is way more informative, then we only need to search the parameter within this prior, and only a few data will do the work. But if we only have an ordinary prior, then we have to search the parameter in a larger space, which requires much more data. So intuitively, if we can improve the quality of our prior, and by quality I mean if it is closer to the true prior, then we can use less data to train a good model. So now we are back to this question. How much data do we need to solve a single task? It turns out we can prove that the information we need to localize the optimum parameter is looking like this. It's actually proportional to the KL divergence between the true prior and our ordinary prior. So this means if we can choose a prior with lower divergence with the true prior, then we need less data. This is consistent with our discussion before. So now our objective is simply minimizing the KL divergence between the true prior and error prior. And if we assume that our prior is parameterized by some alpha, then we only have to optimize the alpha to minimize this KL divergence. So now we only have to define this parameterized prior, but instead of defining it manually, we can actually derive it directly from multitask learning. Because in multitask learning, we normally use a joint training strategy, which means we optimize the main task and auxiliary task together. Here, each auxiliary task is weighted by some alpha k. So this loss is really similar to the single task scenario, and if we compare these two, we can find that we are actually replacing our ordinary prior with this data likelihood of the auxiliary tasks. Here we call this a surrogate prior. So now we seem to have an answer to the question before. How do we decide which auxiliary tasks are more important? Or how do we decide the task weight alpha? It turns out we can simply optimize the alpha to minimize the divergence between the surrogate prior and the true prior. So this would be an automatic way to reweight the auxiliary tasks. So now we only have to design an algorithm to minimize this scale divergence. But this part is actually a bit tricky because we cannot directly minimize this scale divergence. Here are some problems. To begin with, we don't know the true prior here. And second, we don't have any samples to estimate the scale divergence. Because scale divergence is in the form of an estimation, and we need samples to calculate the estimation, but we don't have any. And the second one is it's really hard to estimate this partition function Z alpha. So now I will briefly talk about how can we avoid these problems by designing an approximate algorithm. The first problem is that we don't know the true prior here. And our solution is replace it by something else. Here is our objective, original objective here. Since we don't know the P star, we want to replace it by something we know. And we can notice that P star is actually covered by the data likelihood of the main task. And by covered, I mean that wherever P star is large, the data likelihood will also be large. It makes sense because the data likelihood should be large around the true parameter. So maybe we can replace P star with the data likelihood, and our objective will look like the bottom one. Here PM is proportional to data likelihood. And note that we also change the distribution we sample from to PJ, which corresponds to the joint loss of the main task and auxiliary tasks. We will explain this later. So now with the new objective, does optimizing this new objective also gives an optimal solution to the original objective? The answer is almost yes, because we can prove that the optimal solution of the new objective is also a near optimal solution for the original one. So now we can use the new objective as an approximation. And the second problem is how to get samples from the distribution. An ideal solution is that we can get samples while we are optimizing the loss, because in this way the regular training process won't get affected and it won't introduce any extra cost. Actually, there are some tools to achieve this. It's called Langevin dynamics. It's basically saying that if we inject a Gaussian noise with a certain variance into the gradient, then each time we conduct a gradient descent step, we can get a new sample from the distribution. So with this strong tool, we can do sampling and optimizing at the same time. So this won't be a problem anymore. Now the last problem is that we don't know the partition function Z alpha here. It turns out we can choose another kind of divergence to minimize. This is called Fisher divergence. There are two benefits. using feature divergence instead of KL divergence. The first is that it doesn't need the exact probability, it only needs the gradient of the log probability, which we can get for free when we are doing gradient descent. And note that the gradient doesn't depend on Z alpha, so we don't need to estimate the Z alpha anymore. So it's easier to estimate than the KL divergence. And the second reason is that the feature divergence is actually stronger than KL divergence, which means when we are minimizing feature divergence, we are also reducing KL divergence, which is also a guarantee on our algorithm. So our final objective looks like this bottom one. We also prove that this gives a near optimal solution for the original problem. Please check the paper for more details. Now we can have the final algorithm, which is pretty simple. When the task weights haven't converged, we will first sample theta using arrangement dynamics, and then we update alpha by minimizing the feature divergence, which is the distance between the main task gradient and auxiliary task gradient. It's similar to regular SGD training, only with an extra step to optimize alpha, so it's pretty simple and barely introduces any extra cost. And then when alpha converges, we can do the normal SGD training. For experiments, we have tested our algorithm on semi-supervised learning, multi-level classification, and domain generalization. The first setting is called self-supervised semi-supervised learning, or S4L. This is actually a regular semi-supervised learning setting, only instead of using the semi-supervised algorithms, we use some self-supervised algorithms on unlabeled data. So it's just a kind of semi-supervised learning. Here we tried two datasets, Silverton and SVHN. And for self-supervised methods, we use these two methods, rotate and exemplar. Rotate means that we can rotate an image by a random angle and make the model to predict the angle. And exemplar means we do some random augmentations to an image and make the feature invariant to these augmentations. And here is the results. We compare our algorithm with other reweighting methods in the last block of the left table and also in the right plot. Notably, our algorithm can get a similar result as grid search. Since grid search finds the optimal weights in multiple runs, it means that our method can find the optimal weights in a single run. We also did some experiments on multi-label classification. Here we have the dataset celeb A with many pictures of celebrities. Each image it has 40 labels, for example, the gender, if wearing glasses, smiling or not, and so on. So we randomly choose one label as the main task and the other 39 labels as the auxiliary tasks. And to simulate the data sparse situation, we only use 10% labels in the main task. And here's the results. It seems our algorithm can actually learn better task weights and get better generalization. Also, we list the top 5 relative auxiliary tasks found by our method, and also the top irrelative ones. The task relationship learned by our algorithm also matches the human's intuition. And the last experience is few-shot domain generalization. It's a bit different from traditional domain generalization because in traditional domain generalization, we have some source domains. We have a target domain. We have labeled data for source domains, but we don't have any data, labeled or unlabeled, for target domain. So this can be seen as a multitask learning because the source domains are auxiliary tasks and the target domain is the main task. And here's the results. Baseline means no data in target domain and we just train our model on source domains. If we have 5 labeled images per class in target domain, then we use our algorithm to adjust the weights and get the results as shown as baseline plus RMO. And if we further use the extra data for training classification, for example, in JT and theta, we can have a better result shown as JT plus RMO and theta plus RMO. So to summarize, we start with the key insight that we need less data if we have a high quality prior. And if you are using auxiliary tasks, we can optimize the prior by reweighting the auxiliary tasks. So this gives an automatic way to reweight the tasks. But since a direct optimization is intractable, we design an approximate algorithm with theoretical guarantees. And we tested our algorithm on multiple settings, including semi-supervised learning, multi-level classification, and domain generalization. Finally, I want to thank all my collaborators. This work won't be possible without them. And also thank you for listening.